Hello everyone, let's take a look at our next problem. Given 8 distinguishable rings, let n be the number of possible 5 ring arrangements on the 4 fingers, not the thumb, of one hand. The order of rings on each finger is significant, but it is not required that each finger have a ring. Find the leftmost 3 non-zero digits of n. Oh my goodness, so immediately this sounds like a fairly complicated combinatorial problem. Which is something I sometimes struggle with. Okay, so we have 4 fingers, we have 8 rings in total, and we need to count the number of ways we can put 5 rings on 4 fingers. So my first inclination here is let's forget about the fact that we have 8 rings. Let's imagine we only have 5 rings, because at the end of this, if we just count all the arrangements of 5 rings on 4 fingers, then we'll just have to multiply that result by 8 choose 5. And the order matters. Okay, so now what I'm thinking is we take the 5 rings, we order them, call them 1 to 5, and we put them on each of the 4 fingers one at a time. So this will handle the ordering, or will it? No. No, it won't. If I have 5 rings, how do I count the number of arrangements on the fingers? I wanted to say you put the rings on the fingers one at a time, and you basically are just going to be multiplying together the number of choices you have for each ring, but that does not handle the ordering of the rings. What if we think instead of assigning rings to fingers one at a time, what if we assign fingers to rings one at a time? Oh, but then we have repeated so at the moment, with everything I'm thinking at the moment, the hard thing to keep track of, or the hard thing to sort of account for, is the ordering of the rings on a finger. You know, if all 5 rings are on one finger, there are 5 factorial ways of doing that. If all 4 rings, and there's 4 different ways of 4 different fingers where that could happen. If 4 rings are on a single finger, and 1 ring is on a distinct other finger, how many ways are there of doing that? Well, the lone ring, there are 5 ways of choosing the lone ring. And then four ways of choosing which finger the lone ring goes on. 3 remaining ways of choosing where the cluster of rings go. And 4 factorial ways of arranging those 4 rings. And then things are going to start to get real complicated when we have, say, 2 rings on one finger, 2 rings on another finger, and a single ring on another finger. Oh. I'm trying to think of if there's like a a way of coding this in terms of like a sequence of strings and then just counting how many strings of different particular arrangements there are. But I can't really... Okay, what I'm going to do, I'm going to ignore the fact that we have 8 rings. I'm going to imagine we have only 2 fingers and that we're trying to think of 3 ring arrangements. Okay, so if all 3 are on 1 finger, the number of ways of doing this is 3 factorial times 2, right? 3 factorial ways of ordering the rings, 2 fingers that we could possibly do that on. And then the only other way of doing this is 1 ring separate. So the total number of ways of doing this, well, there are 3 possible rings, which could be the separate one. 2 fingers where the lone ring could go, and then 2 arrangements of the rings on the finger that has 2 rings. So what do we get here? This is 12 total arrangements, and this is also 12 total arrangements, so we get 24. What if we go 4 rings on 2 fingers? So all 4 together is 4 factorial times 2. What if we have 3 together? 3 together gives us, so 4, because there are 4 rings, which could be the lone ring. 2 multiplied by 2, because there are 2 fingers, which could have the lone ring. And then 3 factorial for the number of arrangements of the cluster. I notice again that these numbers are the same. So 4 factorial is 24, times 2 is 48. This number here is also 48. And then what if we have 2 pairs? Okay, so interesting. I don't see, so with the 2 pairs, I don't really see exactly how we could get a 3 out of this, but let's try and figure this out. So I have 4 rings. I put 2 on each finger. How many ways are there of doing that? Well, okay, let's first figure out how many ways there are to divide the 2 rings between the 2 fingers. I suppose that's 4 choose 2. So there's this many ways of dividing the 2 rings into 2 groups. Then we have to multiply by 2, because the first group could go on the first finger or could go on the second finger. Now, once the rings have been assigned to fingers, there are 4 ways of ordering them, because each finger has 2 possible orders. So what is this equal to? This is 4 factorial divided by 4 times 2 times 4, which is again 48. Wild. Okay, what the heck is going on here? So the total here, 48 times 3 is what? 144? Yeah. I'm going to do one more case here, which is, should I do 4 rings on 3 fingers or 5 rings on 2 fingers? So 5 together is 5 factorial times 2. 4 together is, okay, so there's 5 ways of choosing a lone ring. 2 fingers the lone ring could go on. 4 factorial ways of organizing the remaining cluster. Okay, and by the way, here we get 240. This is also equal to 240. And if we have 3 together, okay, so this is good. This is a little more complicated, but I bet you the answer is going to be 240. So 3 together. Okay, so we start with 5 choose 3. So we've divided the 5 rings into 2 groups. Multiply by 2 because group 1 can go on one of the 2 fingers. Then we have to multiply by 3 factorial for the arrangements of the first and 2 factorial for the arrangements of the second. So what do we get here? We get 5 factorial divided by 3 factorial times 2 factorial times 2, which is equal to 240. What is going on? This is what, 720. This is bizarre. So if the pattern is to continue here, 5 rings on 4 fingers, it's a little different though, because now we can divide things into 4 different groups, not just 3. But it should be, is it going to be 5 factorial times 4? Well, that's 5 factorial times 4 will give us like this number. And then we have to multiply by the total number of arrangements going down. Let's try 5 rings on 3 fingers. And it's a bit more complicated now because 5 rings, so when we have 3 fingers, the rings can be divided into 3 groups. So that's not, it's not going to be simple like 5 choose n. It's how do you make multiple groups from a collection of items? Okay, well again, let's just try and figure it out as we go. We'll have 5 factorial times 3. So 120 times 3 is 360. Now if we have 4 together, so there's 5 ways of choosing the lone ring. Now the rings are in 2 groups essentially. We have to choose 2 fingers that they go on. That can be done in 6 ways, including ordering, right? Group 1 can go on finger 1, 2, or 3. Group 2 can go on one of the remaining, and then we get swap. And then we have to multiply by 4 factorial for the arrangements of the cluster. This gives us what? This does not give us 360. This gives us 6 factorial, which I believe is equal to 720. Did I do that right? I think so, yeah. And then there's 3 together, which breaks up into 3 and 2, or 3, 1, and 1. Yeah, so now we're getting complicated enough. I'm worried that when we go to 4 fingers, this case-by-case counting is going to get a little bit complicated. Okay. Slightly different approach. What I'm going to do now is think of 4 fingers. And each of them has space for 5 rings. So I'm kind of thinking in my head again, you know, of assigning the rings to the fingers one at a time. But then I'm worried again about double counting. I'm not sure. This is kind of frustrating. I think I'm going to come back to this at some point after thinking about it in the back of my mind. I feel like there's got to be a way of, like, I don't want to have to break this up into every possible case when there's 4 fingers like this. There's going to be a whole lot more cases of the way that the rings can be grouped. You know, you can get 3 and 2. You can have 2, 2 and 1. You can have 2, 1, 1, 1, 1. I'm sure there's probably some kind of simpler way of setting this problem up and just counting a more straightforward collection of arrangements of something slightly different. But I just don't see it right now. So I think I'll just think about this and come back to it. That's the best I can do for now. Thanks for watching so far. Okay, so I had another thought about how I might approach this problem. And it's kind of related to what I was doing before. But I think, you know, let me just explain what I'm going to do here and why I think this should work. Actually, I'm hoping that it's self-evident that this should work. So we have 4 fingers and we have 5 rings that need to be distributed amongst these fingers. So the first thing I'm going to do is figure out, kind of like what I was doing up here, I'm going to choose a possible grouping of the rings. So for example, if all 5 rings are on a single finger, that's like one grouping. Or if 3 rings are on one finger and 2 rings on another finger, that's another type of grouping. So for any one grouping, I have to figure out how many different ways those can be organized amongst the fingers. And then to handle the permutations that have to do with different orders of rings, we just multiply that by 5 factorial. So I don't have to worry about the orderings of the fingers on any individual finger. Or sorry, I don't have to worry about the orderings of the rings on any individual finger. I just have to take the number of ways the groupings can be distributed amongst the fingers and multiply by 5 factorial. That will handle all of the orderings of the rings on a single finger, but also how individual rings can be interchanged between the fingers. Okay, so first let's figure out how many different ways the five rings can be sort of grouped. So we can have 5 together. We could have a 4 and a 1. We could have 3 and 2. We could have 3, 1, 1. And we could have 2, 2, 1. And 2, 1, 1, 1. I don't think there's any other possible way that the 5 rings can be distributed in groups like this, you know, into a maximum of 4 different groups. And then what I'm going to do here is for any of these groupings, I'm going to count the number of ways that these groups can be distributed distinctly between the fingers. Okay, so a group of 5 rings together, that's basically like a single group of rings. There's only 4 ways of distributing those amongst the fingers. They're either all on one finger or another or another or another. With 4 and 1, it's similar. There's 4 ways of, sorry, not 4 ways of doing this. How many ways are there to do this? 12, right? So think of the 4 and the 1 as being distinct entities. There are 6 ways of choosing which 2 fingers they go on. You know, that's just going to be 4 choose 2, which is equal to 6. But then we have to multiply by 2 to take into account that you might do it the other way around, right? Same thing is going to go with the 3 and 2. If I have one group of 3 and one group of 2, there are 12 different ways that those can be arranged amongst the 4 fingers. 3, 1, and 1. So the way I'm going to think about this is I'm going to determine the 2 fingers that have the 3 and that have the empty, so 3 and 0. That can also be done in 12 ways, right? I'm choosing which 2 fingers have 3 and 0, and then the remaining 2 fingers obviously both have 1. But it's going to be 4 choose 2 times 2 because we have to take into account that we could swap the fingers that have the 3 or that are empty. 2, 2, and 1, again, I'm going to choose the 2 fingers that have either 1 ring or 0 rings. There are 12 ways to do that, and whichever 2 fingers remain will have 2 rings. Then the 2, 1, 1, 1, this can be done in 4 ways, right? Because we simply select one finger which has 2 rings. The other fingers will each have 1, and there's 4 ways of determining the finger that has 2 rings. Okay, so if we add these all up, we get 48 plus 8, which is what? 56. Okay, so 5 rings amongst 4 fingers. Has 56 times 5 factorial arrangements. So 8 rings with 5 on 4 fingers. As I discussed previously, this should have 56 times 5 factorial times 8 choose 5. Okay, so you know, the first step is of the 8 rings, we choose 5 of them. That can be done in exactly this number of ways. Once we have those 5 rings chosen, this is the number of ways those 5 rings can be distributed amongst the 4 fingers. So what is this? This is 56 times 5 factorial times 8 factorial over 5 factorial times 3 factorial. Can I simplify this? What is 56 divided by 2? 28. 28 times 8 factorial divided by 3. And of this number, so this is the number that's been called n in the problem, we have to find the leftmost 3 non-zero digits of n. That's a bit of it's a little crazy, right? Is there an easy way of doing this? Is there an easy way of doing this without just, okay, well, let's call this is 28 times 10 times 8 times 7 times 6 right? The 10 has the 5 and the 2. There's no 3. 8, 7, 6, 5, and times 4. Okay, so 280 times 56 times 24. I'm just going to multiply this out by hand. Okay, so the total number of combinations I get is 386,320. So the answer to this question should be 386. I hope this is correct. Some arithmetic mistakes certainly could be done. A lot of this multiplication ended up being quite a bit bigger than I expected it to be. But all right, that's fine. I'm pretty sure this approach here of just counting up how many possible groupings are possible on the 4 fingers and then multiplying by 5 factorial. I'm pretty sure that should work. But maybe there's a simpler way that allows us to get to this total. The computations here involved products of numbers that were bigger than I expected. So yeah, I'm going to say 386 is the answer here. If I have any more thoughts about this question, or if I find a mistake, I'll include it in the comments below. Thanks for watching.